In this section, we're going to talk about ways we can describe redox equations. So losing electrons is oxidation, and the substance that loses electrons is now called the reducing agent. Gaining electrons is reduction, but the substance that gains the electrons is called the oxidizing agent. Remember, in any redox reaction, electrons are transferred. It's being lost from one reactant and gained by the other. But if you are losing electrons, you're actually going to not only just lose the electrons, you're going to make somebody else gain them. So you are the agent that's doing the reducing. Or if you're gaining electrons, you are, in a way, taking them from the other reactant. So you're the one that's doing the oxidizing. You're making the other reactant become oxidized. So that's why we call it the oxidizing agent. So in the New York State Regents, you're often not only asked to define who was oxidized and who was reduced, but you need to be able to identify who the oxidizing agent and who the reducing agent is. So all you simply need to know is that it's reversed. If you're oxidized, you're the reducing agent, and if you're reduced, you're the oxidizing agent. So let's go back to our initial example here of magnesium plus sulfur makes magnesium sulfide. So let's fill in our oxidation numbers. Magnesium, of course, is 0. Rule number 1, it's uncombined. It's by itself, so it gets a 0. So is sulfur. Next, magnesium is plus 2 because it's in group 2. It can only be plus 2. So that means sulfur must be minus 2 because rule number 5 says their sums need to equal 0. Okay, so let's look at our oxidation numbers here. So magnesium went from 0 to a plus 2. So its oxidation number increased. That means it was oxidized by losing 2 electrons. Next, the sulfur atoms became sulfur ions with a minus 2 oxidation number by gaining 2 electrons. So if you gain electrons, you're reduced. Okay, so if magnesium was oxidized, that makes it the reducing agent. And if sulfur is reduced, that makes it the oxidizing agent. It's as simple as that. All you need to do is first identify who's oxidized, who's reduced, and then label who the reducing and oxidizing agents were. Okay, another thing that you'll be asked to do is to know whether or not a reaction is a redox reaction at all. So remember, the definition of a redox reaction is one in which electrons are transferred in the equation. So one way to do this is to assign oxidation numbers to every element in the question, and if the oxidation numbers change, it's a redox reaction. If the oxidation numbers don't change, it's not a redox reaction. So in the world of chemical equations, there's actually only 2 kinds. There's redox reactions, in which oxidation numbers change, and there's non-redox reactions. So reactions in which there's been no change in oxidation number are not redox reactions. So here's an example. I will save you the trouble of filling in the oxidation numbers, but if you did and went through and assigned them all, such as this, okay, you'll notice that none of the oxidation numbers changed. Silver was a plus 1 on the left, it's a plus 1 on the right. Nitrogen's a plus 5 on the left, plus 5 on the right. Oxygen minus 2, minus 2. Sodium plus 1, plus 1. Chloride minus 1, minus 1. None of the oxidation numbers changed. So you couldn't identify somebody oxidized or reduced because nobody was oxidized or reduced. In actuality, the reason this is not a redox reaction is because it is a double replacement reaction. Double replacement reactions tend not to be redox reactions. So on the Regents, when they ask you to identify the equation from 4 choices that is not a redox reaction, again, you could assign oxidation numbers for everything in all of your choices and look for the one that doesn't change, or you can just remember the simple fact that double replacements are not redox reactions. Okay, let's look at some trends in oxidation and reduction. So this is just some things that you kind of need to know about oxidation and reduction. So we're going to break it down from metals and nonmetals. So metals lose electrons easily. So if you lose electrons, that means you are easily oxidized. And if you're easily oxidized, that makes you a strong reducing agent. In nonmetals, active nonmetals, they gain electrons easily. They have that high electronegativity compared to nonmetals. So if they gain electrons easily, they are very easily reduced. And if you're easily reduced, that makes you a strong oxidizing agent. So another common Regents question is usually asked along the lines of which of the following choices is the strongest reducing agent or the strongest oxidizing agent. And if you know these trends, or you can use table J to judge the activity of metals and nonmetals, these questions should be pretty easy. Okay, so let's do some example problems here of identifying oxidation and reduction in oxidizing agent and reducing agent. So let's do the first one together. So chlorine is 0 because it's a diatomic element, basically uncombined element by itself. So we give it a 0. Next we have HBr. H is +1 because hydrogen's always +1. And so that means bromine must be -1. So their sums will equal 0. And next we have HCl. H is +1, which means chlorine must be -1. So it becomes 0. And we have another diatomic element, which means it is 0. So once we have our oxidation numbers, it's time to decide who was oxidized and who was reduced. So bromine goes from a -1 to a 0. So its oxidation number increased from a negative to 0. So that means bromine was oxidized. Chlorine went from 0 to -1. So its oxidation number went down or was reduced. That means it was reduced. So if chlorine was reduced, that makes it the oxidizing agent. And if bromine was oxidized, that makes it the reducing agent. Okay, next, why don't you try the next one on your own? Carbon plus diatomic oxygen makes carbon dioxide. First step is to assign oxidation numbers, decide who was oxidized and who was reduced, and then label the oxidizing and reducing agents. Okay, carbon is 0 because it's uncombined, so is oxygen. In carbon dioxide, oxygen is a -2, so that means carbon must be a +4. Carbon's oxidation number went up from 0 to +4, so it was oxidized. And oxygen went from 0 to -2, so that means oxygen was reduced. So of course carbon, if it was oxidized, makes it the reducing agent, and if oxygen was reduced, it is the oxidizing agent. Okay, and the last thing I want to show you here is how to write redox half reactions. This is something we'll be using later in this chapter. So a redox half reaction is just a way of simplifying the whole oxidation reduction reaction to just focus on what was being oxidized, or written to just focus on what was being reduced. So the first step is to assign oxidation numbers to every element in the reaction. Then we decide who was oxidized and who was reduced just by looking at those numbers and seeing whose oxidation number went up by losing electrons and whose oxidation number went down by gaining electrons. Then you write a half reaction for the oxidation and reduction separately. So you just focus on what was oxidized and how it was oxidized, or what was reduced and how it was reduced, and ignore everything else. So let me show you how to do that. So in this equation here, nitrogen plus oxygen makes nitrogen monoxide. Your first step is to assign oxidation numbers. So nitrogen gets a 0 because it's diatomic, and so does oxygen. Next, I'm going to put the -2 on oxygen, which means nitrogen must be a +2. Your next step is to figure out who was oxidized. Of course, that is nitrogen. Nitrogen's oxidation number goes from 0 to +2. So its oxidation number went up by losing electrons. So next we're going to write a half reaction just showing what happened to the nitrogen. So nitrogen with its 0 oxidation number turned into nitrogen with its +2 oxidation number. And then I asked myself, how did it do that? Did it do that by gaining electrons or losing electrons? Of course, losing electrons means oxidation. So that means my electrons need to be on the right-hand side of the equation here as a product. So I lost or gave off electrons. And then I need to ask myself, how many electrons does it need to be lost to go from 0 to a +2? And of course, that's 2 electrons. Another way to check yourself is the sum of the charges on the left and the right are always equal. Now they don't always have to be 0, they are in this case, but they have to be the same. So on the left I have 0 for a charge, on the right I have a 2 plus and 2 minus 1s, 2 minuses, 2 plus 2 minus, that's 0 on the right. Okay, next let's do the reduction half reaction. So oxygen was reduced and went from 0 to 2 to minus 2. So I'm just going to focus on how that happened in my half reaction. So I write oxygen with a 0 oxidation number, and then it turns into oxygen with a minus 2 oxidation number. And I ask myself, how did it do this? By gaining or losing electrons? And of course it gained electrons. So that's why I left some space here. You may figure this out later. You could write it on the left or you could write it on the right. It doesn't matter, but it has to be on the left-hand side of the arrow. So this oxygen atom is going to be gaining 2 negative electrons to turn into oxygen with a minus 2 oxidation state. Okay, so now you try. In this equation here, first step is to assign your oxidation numbers. Figure out who was oxidized, who was reduced, and then write the half reaction just showing that. So go ahead and pause it and give it a try, and when you're ready, I'll show you how to do it. Okay, so first step is to assign your oxidation numbers. Zinc gets a 0 because it's by itself. This hydrogen ion gets a +1 because its oxidation number is equal to its charge as a +1 charge. So it has a +1 oxidation state. Same thing for this zinc ion, gets a +2 charge. And of course hydrogen at the end here gets a 0 because it's diatomic. So let's figure out who was oxidized. So the zinc goes from 0 to a +2. So its oxidation number increased, so that means zinc was oxidized. So I'm going to write zinc with its 0 turns into zinc with its 2 plus, or its a +2 oxidation state, and then I ask myself, how did it do that? It did that by losing electrons. If I lose 2 negative charges, so I would show that as a product on the right, I get a +2 oxidation state, or a +2 charge in my final product here. Next is the reduction half reaction. If zinc was oxidized, that means hydrogen ion was reduced. It went from a +1 to a 0. So it did that by gaining electrons. So it gained 2 electrons here. So it says a 2 because this hydrogen has a little 2 in front of it. So I have 2 hydrogen ions, so 2 +1s need to be balanced out by 2 negative electrons to become a 0 oxidation state here. So another thing that can help you determine whether you did it right is the oxidation, or the electrons lost need to equal the electrons gained in any chemical reaction, in any redox reaction. So if I very easily determine that this was 2 just by looking at the charges, that would clue me in that this has to be 2 as well. So it needs to be written as such. Okay, so let's sum things up here. The reducing agent is the reactant in your redox reaction that was oxidized. So if you can identify who is oxidized, you should be able to easily identify who the reducing agent is. And it's the reverse for the oxidizing agent. The oxidizing agent is the reactant that was reduced. Remember, if oxidation numbers don't change, then the reaction is not a redox reaction. This is typically in double replacement reactions. All other types of reactions, barring a couple of rare examples, are redox reactions. You should also be able to write a half reaction, which describes just the oxidation or reduction that takes place in a chemical reaction. In oxidation half reactions, electrons are always on the right because they are losing electrons as products. They are given off in the reaction. In a reduction half reaction, the electrons are always on the left because electrons are gained as reactants in reduction half reactions. And also when writing half reactions, the sum of the oxidation numbers on the left need to be equal to those on the right. So that's a way to double check yourself to make sure you did it correct. Of course, as many things, this requires a lot of practice. So we'll be doing a lot more half reaction practices in class. So if you are having a little trouble, That's okay, we're going to go over it in class. But if you have any specific questions, please write them down and let me know.